Hi all. Today we'll talk about bringing together all the techniques that we've learned so far into a strategy for integration. And unfortunately, we don't have the recipe for integrating an arbitrary function. Strategy is the best that we can come up with, and the strategy will not be a unified algorithm, but a bunch of techniques, a bunch of recipes which work in particular cases. Unfortunately, but that's the situation with most of science anyway. You have to be creative to apply the known techniques, and that's exactly the case with integration. But the basis for all of them is, of course, the table of standard integrals that we should know by heart. Here it is. Um, Studied, most of it is, of course, the derivative table read backwards. So if we follow the derivative table backwards, then we'll come up with most of the formulas, but some of them are actually a little harder than others. For instance, you don't necessarily have to remember the last one the last two, oops, if you have an idea of what an arctangent does, then if you remember the 1 over x squared plus 1 is equal dx as it gives you arctan, then that's good enough. And then you can manipulate that to get you the last one, number 17. And similarly for 18. Again, if you just remember that 1 over the square root of 1 minus x squared dx will give you arc sine, then you can figure out how to get 18 by manipulating this one into the standard integral. Okay, what is the next level of sophistication? Of course, after that, we'll fall onto the basic techniques for integration, which are, so next, beyond these, are the two main techniques of integration, which are integration by parts and U substitution, integration by U sum. Okay, but before you apply those, take a careful look at your integrand, and maybe you will see that you can just simplify it. So even before looking for obvious use up for integration by parts, before that, maybe you can simplify the integrand. So here's an example. Let's say that we have to look at something like, I don't know, x cubed minus cube root of x divided by square root of x times x dx. Looks pretty intimidating, and it doesn't look like any of the techniques that we've seen before apply. It's not a product, it's not a rational function either. But if you simplify, just do some algebra. What can you get here? If you just write it as x cubed over x to which power do we have on the bottom? 1 plus another 1/2, 3/2, minus x to the 1/3 over x 3/2. Then it starts looking better. We'll get the integral of x. 3 minus 3 halves will give you 3 halves. And here 1/3 minus 3 halves. What is that? Common denominator is 6. So you will get how many 6? You'll get 2 minus 9/6 dx. And then you can split it into the integral of 3 halves dx minus the integral of -7/6 dx. What are the antiderivatives? Of course, all you have to do is to use the power rule in reverse. So you are adding 1 to get 5 halves, multiply by 2/5. And here you would add 1 to get -6, multiply by -6, plus c. Check it if you like. You will see that that's correct. So finally, we will write it as 5 halves plus 6x to the 1, 6 plus c. Okay, so that is one way to simplify the integrand. Then the next obvious technique is, of course, check for one of the basic two u substitution or integration by parts. So u sub. Maybe there is an obvious u sub in there already. So again, what's a good example of that? But don't try too hard. If it's obvious, yeah, use it. If not, then maybe you have to spend some more time strategizing. You will soon figure out that in this situation, it pays to spend some quality time in the beginning of the problem to see what works and what is less likely to work, because you usually won't have unlimited time to try all of them, to throw all of the techniques at your integral. You want to spend some time strategizing. So u sub, is it obvious before you run to apply it? So let's take a look at another fraction. So let's say that we have, let's say x cubed on the bottom, plus 2, and then on the top something like x squared. Is u sub obvious here? If you think about it, pretty obvious. Should you treat it as a rational function instead? I suppose you could solve it as a rational function, partial fraction decomposition. That would be very complicated. So it does pay to think about the possibilities. And if you spotted, if you thought about it as a rational function first, maybe it would pay off to think a little bit more and notice this obvious, or maybe not so obvious, u sub. So is it obvious? What should be your u here? Of course, the bottom expression x cubed plus 2. Right, du is 3x squared dx. And pretty much you see that on the top, up to this 3, which is missing, but you really need it. You can create it. So you can say one way to do it is to say that x squared dx that you do see on the top is 1/3 du. So that the top becomes 1/3 du and the bottom is just your u. So 1/3 logarithm. Don't forget the absolute value of u. In the original terms, you have to convert to the original variable. It will become x cubed plus 2 plus c. And that's it. Next technique. What else can we do? We can try and now, if the obvious U substitution doesn't work, we can try and classify what do we see under the integral. What kind of function is it? So maybe we want to classify. All right, classify what's under the integral. What's the integrand like as a function? Well, we spent quite a lot of time looking at products. So does it look like a product? What kind of a product? Or does it look like a ratio? Are we dealing with a rational function? Is it a ratio of polynomials? We can just as well start with a trig function. So does it look like a trig function? So if so, then we'll use the techniques from trigonometric integrals. So use trigonometric integral techniques. They allow you to deal with product of sines and cosines or secants and tangents. Then if it is a ratio, so maybe it's a rational function, then we would use partial fractions technique. Maybe it's a product of two terms. What kind of product? If it's a product of unlike terms, say polynomial and a trigonometric function, e.g. integral x sine x, what will you use then? If these are unlike terms, look for integration by parts. Try integration by parts. What else? What if this is the product of two terms which are like? Maybe one you see a derivative of second term being a derivative of some part of the first term, then you're looking at the U sub, and that we already discussed. What if you see radicals? It depends what's under the radical. If you see a quadratic expression, radical of something quadratic in x, something like square root of plus or minus x squared minus or plus or minus a squared, then use trigonometric substitution. Remember, you had the choice of setting x to dependent on a particular combination of pluses and minuses to maybe secant t, or a times secant t, or a sine t, or a tangent t. What if it's not quadratic? What if it's linear? Linear in x. And this could be any radical, power n, e.g. third root of ax plus b. Then just take that as your u. And that is known as a rationalizing substitution. Can you guess why? Since it makes your integrand into a rational function. And sometimes, even if you have something more complicated, like say some arbitrary function, not quadratic, not linear, some g of x, not guaranteed, but try to use u sub. And if neither of this works, then be persistent, try again. So if not, then try again. Sometimes it will take two separate techniques applied consecutively, one after another, to achieve the integration. Okay, so try substitution again, try parts again. The basic two techniques are substitution or parts. So maybe U sub or trigonometric sub. Trig sub or parts, or you may try and do some algebra. So that would not necessarily classify as simplifying. In fact, you may need to make it more complicated than what you began, what you started with. So we will not say simplify, we'll say use some algebraic manipulation. So algebraic manipulation. Let's give an example here. So for instance, the integral, what do I want to look at, dx, let's say you have 1 plus sine x. How would you approach this one? Nothing obvious comes to mind, but why don't you multiply top and the bottom, as you've seen so many times in your intermediate algebra, hopefully, by a conjugate. What's a conjugate? Similar expression where you have negative sign, 1 minus sine x, 1 minus sine x, dx. So on the top you will get 1 minus sine x, on the bottom you will get 1 minus sine squared x. So does it help you? Well, if you simplify the bottom using the fundamental identity of trig, you'll get cosine squared x, 1 minus sine x on the top. So you'll get cosecant squared x minus tangent x times cosecant x dx. That's one way to think about it. Or another way to think about it is just leave as it is, sine x over cosine squared x dx. And if you split it into two, then the first integral is the standard one, isn't it? So derivative of tangent is secant squared. What am I saying? So this is the secant squared, right? That we have y cosecant, of course, secant. So secant squared x. And let's convert the second one as well. So derivative of tangent is secant squared. And the second integral will be the integral of tangent x times secant x dx. So the first one was standard. Actually, the second one is also not a standard, but still a trigonometric integral. So finish on your own. Maybe one more hint. Well, you use the trigonometric integral here, though. You don't have enough powers of to convert from one to another. So maybe it's just better to leave it as it is and integrate from here by a u sub. So I will leave it for you to finish, but the hint is use a u sub. Finish yourself by a use of a u sub. And what's your u sub? Of course, cosine x. Okay, du and good. So algebraic manipulation helps, even if it's less than obvious sometimes. Sometimes you can also fall back on the previous problem, fall back on a previously solved question problem. So here's an example. Let's say that we want to integrate tangent squared x secant x dx. Maybe not so obvious what to do, but if you use a trig identity relating tangent and secant, so tangent squared plus 1 is secant squared, so we can say that secant squared minus 1 is the tangent. Multiplied by the remaining secant, and what do you see here? You see secant cube after you distribute the secant on the left and on the right. Integrate that minus the integral of the secant. But we've seen how to do the first one before, and the second one is the standard. Maybe not the most standard one, but it's in the table. You should remember how to do it. So again, I'll leave for you to finish. I don't recommend memorizing secant cube, but integral of secant you should be able to derive. And secant cube, if you've forgotten, then just do it, right? Okay, so finish yourself. And sometimes you will, just as I said, you'll have to use a bunch of techniques together, but usually if you're using more than 3, then likely that something went awry. Usually a couple of techniques will get you where you want to be. Let's look at one more example. And that is this same looking integral with tangent, but now cosine is on the bottom, cosine x cube. So what do we make out of it? Should we recognize the cube and divide tangent over cosine? Well, that doesn't give you anything promising. How about Frequently, if you're lost with integral containing trigonometric functions, it may be useful to just reduce it to the basic sines and cosines. So let's try to do that. We'll have sine cube over cosine cube, and another cosine cube will give us cosine 6 of x dx. And then you may make a connection with this one. How did we tackle this one? By splitting off, right, by using this substitution. Splitting off one of the odd powers. So the odd power here is on the side, so why don't we split that off? We'll have sine squared x sine x dx over cosine 6x. So if we try for a u sub, which will give us sine x dx as du, it doesn't take long to figure out that u should be cosine x. Well, up to a minus, we'll get the minus here. So then it follows that what we have on the top, sine x dx, will be negative du, right? This part is going to be negative du. So then what do we make of sine squared? Of course, 1 minus cosine squared. That is 1 minus u squared. So that's the top, and what do we make of the bottom? U to the 6. After that, it's all easy if we notice that we can just simplify the integral, simplify the algebra under the integral to make it into u negative 4 minus u negative 6 du. So what do we get? After we integrate, let's finish the integration. We'll have u minus third divided by negative 3 minus u minus fifth divided by negative 5 plus c. So to finish, we'll just convert to u, which is cosine x. So we can put cosine cube x on the bottom plus 1/5 cosine 5th x on the bottom plus c. Maybe a little bit more elegant is to start with the highest power. And that's the final answer. Good. So we'll see a lot more examples in the class, and the focus here will be on applying the appropriate technique rather than solving in all details. Maybe let me give you a couple more so that you can start thinking about them. So question will be not necessarily to go through completion, but stop as soon as you understand, as soon as you are sure what to do in this case. So one example will be integral of e square root of x dx. Try this. Also try the integral on something a little bit more complicated. X fifth plus 1 over x cubed minus 3x squared minus 10x dx. Okay. That's it for today. See you guys in class. Take care.